This is the second portion of the lecture on the brain. This second portion is given on Thursday, October 15th. In the second part of the brain, we're going to look at the cerebral cortex. This is the outer layer of the brain, and it makes up most of the forebrain. This is where most of the advanced types of thinking occur. Our brain can be split into two hemispheres, left and right. Now, what's kind of interesting about the right and left hemisphere is that each side can operate independently. So while the right hemisphere is conducting some sort of action, the left hemisphere can also conduct an opposite and completely different reaction. Additionally, the one other thing that's kind of interesting about the hemispheres is that when the hemispheres are sending signals down to our body, it always sends it from the opposite side. So when I move my right hand, it's my left hemisphere that's being active. And when I wink my left eye, it's my right hemisphere that's being active. The brain has a structure that allows for signals to pass between the two hemispheres, and also provides a sort of tissue connection between those two hemispheres, and that's called the corpus callosum. It exists in the outer layer and is the part of the brain that connects the two sides of the brain, the left and the right, and allows for signals to pass between the two. The cerebral cortex can also be split into four distinct lobes. Each lobe has two parts, one for each hemisphere. The frontal lobe is the part of the brain that's located right behind the forehead. It's in the blue that you can see here. The parietal lobe is in the top and back part of our head. You can see it here in the green. The occipital lobe is in the back and bottom of our head. You can see it in the pink. It's that smaller one. And then the temporal lobe is on the sides of our head above our ears, which an easy way to try to remember that is it pretty much starts where our temples are. Some of the more basic things that the cerebral cortex does is have subcortexes or cortices. These subcortices are instrumental in us receiving signals from our senses. At the very back of the frontal lobe is the somatosensory cortex, which you can see here in yellow. The somatosensory cortex is where our brain experiences touch. Now, just like I mentioned before, when we get touched on the right side of our body, like let's say someone gave me a high five on my right hand, then we would experience it on the left side of our somatosensory cortex. Additionally, another thing that's pretty interesting about the somatosensory cortex is that the amount of cortex that is active is dependent on the sensitivity of a limb. So as you can see here in this diagram, a good chunk of the brain activity in this cortex is devoted to our face, to our thumbs, to our fingers, and to other parts of our face, like our jaw and our tongue. This is because those parts are so sensitive, and yet bigger limbs like our trunk, our hips, our knees, our legs, they're not as sensitive. They can take more pain or more damage without feeling pain because less of the cortex gets active. At the very front of the parietal lobe is the motor cortex. The motor cortex is the way that the brain sends signals out to make our muscles move. So when we want to make our left thumb move, we are going to use the right side of our motor cortex. Our motor cortex also is kind of interesting because each hemisphere can send out signals independent of one another. So we can move our right hand and our left hand at the same time. But what's kind of interesting is that we can't send out conflicting signals on the same side. So if you tried to move your hand in a clockwise motion and try to move your ankle in a counterclockwise motion on the same side, let's say it's your right hand and right ankle, you're not going to be able to do it. But you will be able to do that with your right hand and your left ankle because each hemisphere can send out signals independent. In the occipital lobe, we have the visual cortex. The visual cortex is where we experience our sense of sight. We can also experience sights that our eyes don't see in the visual cortex if there is some sort of disease or damage or chemical changes to the cortex or even trauma to the cortex, which will create what we call hallucinations, which are sensory signals that our eyes don't see. So if someone hit a person in the back of the head with a baseball bat, that person would see stars. But their eyes wouldn't be seeing stars. It would be the trauma to the cortex that caused them to see that. Directly above our ears is the auditory cortex. The auditory cortex is most well known for our ability to hear. So very similar to the visual cortex, when we receive signals from our ears, it goes to our thalamus, and then the thalamus sends it to the auditory cortex where we experience hearing. Now you'll notice that there's a lot of the cerebral cortex, that outer layer, that isn't highlighted with color, that isn't one of these cortexes. That's because the rest of the cerebral cortex serves as what we call association areas, where we do some of our most advanced planning and our most advanced mental skills. In the frontal lobe, the association areas are connected to judgment, planning, and processing. So judgment, consequence, planning, making plans, and evaluating consequences. This is the last part of the brain to fully develop when we hit about 25. So when teenagers and younger 20-year-olds sometimes do stupid stuff, it might be because they're not evaluating the consequences properly. The association areas of our occipital lobe are instrumental within our personality. The association areas of our parietal lobe allow us to be good at math and spatial reasoning. So things like math skills, but also the ability to manipulate an object in space or visualize a space to manipulate an object. Like if you had to pack a trunk of a car and had to fit a bunch of suitcases in it, your spatial reasoning will allow you to do that. And then finally, the association areas of our temporal lobe allow for recognition of faces. So while if we didn't have this, or if we had damage to this, while we would still be able to recognize specific characteristics in people's faces, we wouldn't be able to connect it to any individuals. Probably no better way to explain just how immensely powerful the brain is by looking at language. Now, I'm not going to ask you to know the various different parts of the brain that are associated with language, but this just does a really good job of demonstrating how advanced and how many tasks the brain can take on all at once. If you're reading that note, the brain breaks tasks down, you're using your visual cortex. Your angular gyrus, which is an association area in the temporal lobe, will transform those squiggly lines that we know as letters into a sound that we hear in our head, in our internal monologue. Another area called Wernicke's area will interpret that code. So we'll change it to just a bunch of sounds to allow for meaning. So now those sounds then create meaning. And then if we're going to speak it out loud, we'd use another area called Broca's area, which would then work with the motor cortex to move the muscles in our mouth and our jaw to allow for speaking the language. So this just goes to show you that this is constantly occurring whenever we're listening to language, whenever we're seeing language, whenever we're speaking language. Multiple parts of our brain are very active all at the same time. But our brain is constantly changing. Plasticity is this idea that our brain alters due to experience. And when we talked about the neural networks in the previous lecture, we talked about how our neurons form new pathways and new connections. Now, what allows for plasticity? Well, children have better plasticity than adults because they can form those networks easier and better. But adults can have good plasticity too if they have great mental stimulation, good social interaction, emotional health, physical exercise, nutrition, sleep. All of these are a healthy lifestyle, which will allow for better cognitive ability, better ability to think, better everyday functioning, and will allow the brain to adjust to experience a lot better. But if a person has a non-healthy lifestyle, social isolation, emotional health, inadequate nutrition or sleep, substance abuse, that will inhibit the ability for the neurons to develop connections and pathways, which will lead to poorer cognitive ability and poorer everyday functioning. Sometimes with damage, if the person experiences brain damage through trauma or a disease, sometimes, though not always, the brain can reorganize through plasticity. Plasticity will allow the brain to reassign tasks. So whereas one structure might be associated with a certain behavior or a certain feeling, with plasticity, if a person experiences brain damage, then they're going to have the ability to maybe take some of those functions on, but in a different part of their brain. Again, this is more likely to occur in children or people who live healthier lifestyles. Finally, the last thing we're going to take a look at here is an idea called dual processing. Dual processing is this idea that our brain works on two levels, the conscious level and the unconscious level. Conscious level would be anything that you're aware of and that you're noticing. The unconscious level would be all those things that our brain still takes in and yet we don't notice at the same time. Imagine we were watching a hummingbird right outside our window. We would see that hummingbird and as a bird, yet our brain would take in shapes like the form, the color, the individual movements, where we're not really paying attention to that because we're just seeing a bird because that's what we're aware of. Our brain is taking in all those other things. And we take in a lot more unconsciously than we do consciously. Finally, the last thing is that there's this idea called left-right brain theory, but this is an idea that's been misinterpreted in popular culture. But the idea in left-right brain theory is that each side of our brain is more dominant in certain tasks than others. Now, this is a true statement, but we use both sides of our brain in every task that we do. Just one side tends to be a little bit more dominant. However, popular culture has made it seem like we only use one side of our brain, or a person is only right or left brained, or only right or left brain dominant. If a person only used one side of their brain, they would be dead. So, if they were dominant in one side of their brain, they probably wouldn't function very well. Both sides of our brain works for every task we do. Just one side is more dominant in certain tasks. But even if a person is more likely to do those certain tasks, it doesn't mean that their brain is dominant in that way because they're still carrying out tasks from the other side as well. They're just not aware of it or thinking about it. But even so, despite this misinterpretation, the idea that one side is a little bit more dominant in certain behaviors is definitely something that is accepted in truth. So here's the two sides. The left side is our logical side. It's in our logical side that we do things like critical thinking, use cause and effect relationships, evaluate numbers, interpret language, and so on. The right side of our brain is the artistic side. This is where we recognize faces and express emotions, things that aren't based on step-by-step type of sequences, music, color, creativity, images, and so on. That is the end of the lecture. I hope that this has given you more insight into the various structures of the brain and what they do.